Good morning, everyone. Sorry I'm late. Good morning. Okay, so the exam has been posted on Canvas. It's available at 10 today. So what will happen is we'll have a lecture, until around then. You can take a break if you want to. Then I will assign you to breakout room. So each of you is in your room. No one will see your camera. And then you will turn on the camera, and then you can take the exam until 11:40, or a little bit after that. All right. And then after you're done, you're just gonna scan the exam and upload it to the Canvas, midterm one, like you do your homework. Is that okay? All right. Any questions in general that we have? All right. So let's begin our lecture today. So one thing I want to talk about first is the implied volatility from last time. Right. And I guess it's interesting, right, as an exercise to see that to find the implied volatility is not just about, so it's the sigma implied, right? Such that the Black-Scholes formula, for example, right, with S0 KRT and sigma implied is equal to the call option market price. Okay. And so what's interesting is you see, like, this is kind of straightforward mathematically, but to decide, for example, right, this T right here, we need some tools, right, like counting how many business days remaining until the expiration. This R right here, right, also causes a little bit of hiccup, because how the Fed, right, gives the R in terms of, so R, right, is given in terms of basis point. And 1 basis point basically is 0.01, right, percent. All right. And so how to say this, right? So basically, there are, what I want to remark is there are like kind of like certain things that you only learn when you really work on certain problems, right? These are practical stuff that there's no way you can think about them, only comes from experience. Well, I may say, right, that so a lot of us use R equals to 5%, like last time, right? 5 to 7%. When you come to think about it, 5 to 7% may not make sense realistically. Why so? Because the duration of our kind of time, right, is only 3 months. And I think you're aware of the concept of term structure, right? Term structure means that basically the interest rate you have to pay depends on how long, right, the loan period is. So basically R at least depends on T, where T is the length of the remaining time for the loan to mature. So for example, if you are like, if you buy like a 30-year bond, then the interest rate available to you annually should be higher than if you buy only a 10-year bond, right? So for one thing, R is always quoted annually, okay? So that makes sense because you don't want to compare apples to oranges. But second, like for different, right, term to maturity, you have different R. So with that concept in mind, I would be suspicious if the borrowing period is 3 months, which is really short when you think about it, right? So basically, the favorite graph, right, of the term structure is, this is T, right? So this is time to maturity, and this is R. And the graph may look like this, right? Where you have like something like 1 month, 3 months, right? All the way to 30 years. Okay. And actually, if you look at the Fed chart, it exactly gives a numerical value for this kind of thing. What I'm saying is, like, when we're in this area, if you think that we're in the 5% area, that would be a super high interest rate. Because if we're in 5% for 3 months, then how much will we pay for like 12 months? How much will we pay for 30 years? Does that make sense? Right? So, and by the way, by 5%, I obviously don't mean 5% for the whole 3 months, 5% annually applied to 3 months. But anyway, but you get the point. So things like this may be, right, a favorite aspect of an interview in the sense that, right, the interviewer wants to know if you're aware of, I don't know, the realistic side of finance, right? Do you feel that your computation makes sense rather than, just apply the formula in an academic way, okay? So again, I mean, I just want to bring up this point to say that, if you make this mistake, it's not because logically you're not sound, but it's because you lack experience in, being exposed to these market concepts or applying, the concepts to real life problem. Okay, so but that is one of the things that the recruiter looks for. Okay, so this should be right 0.05%, 5 point basis. Any question on this? All right. So the second one, right, then that would, the second concept I want to mention in connection with this is the volatility smile. Again, right, a very practical concept, an applied concept. It has no rhyme or reason in terms of logic. But again, a very super important concept that you may be asked on an interview. I don't know. But does anyone know what volatility smile is? What does it refer to? So the volatility smile, right, refers to the idea that, when you solve for this, right, it's not the end of the story. It's not the end of the story. How? Because again, it probably is, kind of connection to practice. But let me show you, right? If you go on, like, if you read a option chain, like Yahoo Finance, for example. Okay, so let's see here. All right, so you see that basically there are a lot of options quoted at different prices, right? Different strikes. There's not only one single option that we look at. Second of all, right? So, okay, what is the current price right now? The current price right now is 2,000, right? 2,000 something, 2,070 for Google. And for very low strike, right? Notice they say implied volatility is 0%. Is that true? Is that really that the implied volatility is 0% for this low strike? Do you see what's going on here with things around this range, for example? And you see, right, basically what I'm trying to say, first of all, is notice that options never given alone at a single strike, right? So this is for the February 26th expiration, so in 2 days. You can go out a little bit further, right, to June, for example. Right, and so notice, like some of them has this kind of weird implied volatility, and some of them has 0%. What's going on out here? And then, right, you see that as a strike goes up, you get different, right? So this is, and also by the way, right, this is the bid-ask spread that we talk about, right? Notice how the bid is always below the ask, right? So the difference right here, so 10 bucks, for example, 10 bucks, right? Right here are the bid-ask spread around this level. So do you notice something interesting for very low strike level of the option? So for very low strike, notice that the volume, right? Volume means it tells you roughly how much it has been kind of traded. It is not really actively traded, okay, for very low strike. And that probably is a reason why. So this is like really deep out of the money, okay? When you think about it, people don't really actively trade option deep out of the money or deep in the sorry, this deep in the money, right? The people don't actively trade options that deep in the money or deep out of the money, because basically there's nothing happening there, right? If it's deep in the money, the delta is close to 1, and so you got 1-to-1 ratio, right? So for these ones, right, basically I would say that it's not actively, they are not actively traded. So the implied volatility, that kind of information is not very much reliable. So we probably will ignore them. Some traders will be interested in, super, deep in or deep out of the money, extreme range like this. But for us, it's probably better to look at right here, the mid range. You see right here. You see, this is where the strikes level is closer. You see, it starts to get more stable, right? The strike level gets closer to the level of the stock price. Okay, so around this level, that basically the options are more actively traded. Look at the volumes, right? Look at the volumes. Okay, and so if you look at the implied volatility quoted around this, it may be more reliable. Okay, and so what happens is you see that the implied volatility changes as a function of the strike. The implied volatility changes as a function of the strike. Okay, so it's not like you get one single implied volatility for even, right, one single stock on that expiration day, and then you're done. It's different implied volatilities for different strikes, for example, right? And so what that tells us, first of all, what that tells us, right, is implied volatility as a function of a strike is something we may be interested in, and usually it follows this kind of graph, okay, a parabola. But somehow, because it looks like a smile, people say this is the volatility smile. Okay. So it's the concept that says that implied volatility as a function of strike is not a flat line, right? It's like this, which kind of makes sense. You see, for basically a little bit deep in the money or deep out of the money, right? The implied volatility is higher than the implied volatility at around, at the money level. All right. Now, of course, does that make sense? So first of all, right, one thing you can check, and one thing I will assign you to do is to try to plot the volatility, implied volatility versus strike graph for a particular expiration day. Okay, and when you plot this, you will observe some graph like this or not. So you would try to verify the implied volatility, verify the volatility smile phenomenon. But what I'm trying to say is, right, Black-Scholes formula will never tell you that this thing exists or not, because this comes from the market price. Okay, this comes from the market price. This comes from how the market is telling you at the moment how the implied volatility should be. So there's no way I can simulate something for you on Python, for example, and say, look, this is a volatility smile. You have to realistically go out there and look at a real option price and see if the volatility smile happens or not. Okay, or how severe the smile is. Sometimes the smile is flat, and sometimes it goes like this. Even they call it a smirk, right? So all these are financial concepts that, right, we use the quantitative tool, namely solving this, to verify, right, a chart like this, a graph like this. And again, the shape of the graph tells, right, the customer, the trader, the information on how, right, the market is acting at that current moment, right? So it makes sense that the smile is probably when market's normal. When it turns to a smirk, you should worry, right? Or things are not normal. For example, right, this term structure graph usually goes like this, but sometimes, right, the term structure graph becomes like in an inverted shape or something like this. Then again, right, that tells something different, if something unusual is happening in the bond market, right? If it has a shape like this. And so trader, right, or market participants actively watch this kind of graph, this kind of shape, to see, right, if there's something fundamental is changing, right? But my point is, it's not enough for you just to kind of study the quantitative tools and ignore, for example, right, or not be aware of the financial implication of what these tools are doing. And so you want to kind of be exposed to that and try to wrap your brain around it. It's not easy, right? But the more you do it, the more you will kind of get a sense of what's going on. Any question? So connected with the volatility smile, right, there's even one more concept called the volatility surface. All right. And rather than just like a phenomenon, volatility surface is a tool that the trader does actually watch every single day or every single hour, whatever. So you can see, right, that volatility surface is a generalization of the volatility smile, in the sense that actually you see implied volatility is not simply a function of strike. It also, from that level, a function of time to maturity, right? Short-term option, right? Option that's gonna mature, gonna expire very soon, right? 2 days option should have a different, right, smile or whatever phenomenon than a long-term option that has 3 months, 6 months out to mature, right? So exactly the term structure kind of quality of the volatility. So for that reason, usually, right, volatility is exhibited as a function of two variables. One of them is time to maturity. One of them is moneyness. Okay. And so you see, it's not really simply it's not simply at a strike level like this. I mean, when you do a single volatility smile, you fix everything else. You fix everything else. So you can let the strike runs and that's fine. But in general, you see, it doesn't make sense for you to let the strike runs because what range of the strike is reasonable, right? Remember, I pointed out to you on the Yahoo Finance chart that when you go too deep in the money or deep out of the money, there's not much action going on. There's not much trading going on. So when you do this, right? So at around 1, right, or actually around 0, right, is when the S equal to K. That's when the option is at the money. And so you have a uniform scale to graph, right, the moneyness of the option. And so this is why people prefer this as a scale to graph rather than just strike, okay? But anyway, right, this will be a graph. This will be a 3D surface, right? It will be a 3D surface or rather 2D surface, whatever, right? I mean, by 2D, I mean two-dimensional surface in the three-dimensional space, right? And so if you fix a time to maturity, you might see something like this, right? Different smiles. But that's not guaranteed, right? That's not guaranteed. If you fix, right, if you slide it around the time to maturity, you might get something like this. But if you fix each moneyness, right, and you look at the implied volatility as a function of time to maturity, then, you know, I guess it's a different phenomenon, which I'm not very sure how it looks. For example, right, again, for a fixed moneyness, how does the implied volatility act as time to maturity goes out, right? I think there is a rule, there's empirical rule there, which I'm not aware of. But again, right, so all in all, right, the volatility surface gives a whole structure of how, right, basically that company is doing in their risk profile. Yes. And so trader, right, or quant, right, would look at the entire volatility surface. And for them, basically, the volatility surface tells you everything about the option price. Because, right, from the implied volatility, you can plug them back into the Black-Scholes formula and figure out what the price is. And so there will be a concept called interpolation, where, right, for example, if you have the volatility surface constructed, and you want to price at a certain moneyness and at a certain time to maturity, then you just try to find what the value of the implied volatility is at that point, and then you plug back into the Black-Scholes formula and figure out your market price. Okay, so knowing the volatility surface is the same as knowing the option price, for example. So, tools like Bloomberg Station would readily spit out the entire volatility surface for you. For any well-known name option. So yeah, basically these things are already kind of automated as a tool for standard day-to-day practice for trader, like on Bloomberg Station. Okay, so but of course, someone has to maintain, right, these things, these tools, and also someone, right, I mean, like has to code it, had to code them, right, at some point. So that's where the quant work comes in, right? Maintaining this, updating them, and of course, maybe code something new for a new product, for example. Okay, but these are very important concepts that I hope you will have a chance to play with at some point. I think constructing the volatility surface may be a little bit, it's not that hard in terms of coding, but notice that when you try to mess around with this, right, data management is one of the challenge. because you need to somehow you should have a reasonable way to import, right, the whole structure of the market price into your program before you can solve the equation. Right? I mean, I think I'll ask you to do this manually because, I'm not going to ask you to find too many option price, maybe 10 option price, and just read them off. But like the practical way to do it is you want to import, right, the whole like kind of Yahoo Finance chart into your program and then read it off and then, right, solve the equation. So here you want to read a lot of option prices, right, at different time to maturity into your program before you can start solving the equation. So how to kind of interface, right, your program with the data given online or from Bloomberg station, and then pull them back into your program and then solve them there. Is more of the technical issue as far as I know. So database, right, is another thing that will come up, how to interact with the database rather than like solving the mathematical aspect here. So that for me is something that would be challenging, that I don't know how to kind of address easily. Okay, I know more about the math than the computer science aspect. But that's just to kind of show you, right, that there are many aspects to come into like kind of working in this kind of fields and come up with this kind of product. So, but you must play around with it to get an idea. Any question? Okay, so that is enough about Black-Scholes. Okay, so we will kind of still, I mean, well, we're going to leave the Black-Scholes world for a little bit and go for the extension. All right. So extension of Black-Scholes model, the one I have in mind is the jump process, right, kind of model. So the idea is that now, before, what we have is stock model like this. Okay, so it gives us something nice. In other words, it gives us that the percentage return has mean mu, has variance sigma square, and is normally distributed. So we have random, right? Random percentage return. Right, normally distributed. But on the other hand, because the Brownian motion is continuous, the returns and also, the stock price, right, are continuous functions of time. All right. So in other words, if you watch the time moves, the stock price or the returns, right, has no jump, no shock, right? No jump, no shock. But when you observe, right, real life market data, you see that sometimes there's a market shock coming in. In other words, you do observe that sometimes, right, and usually maybe it happens more with crash than jump up, but you may observe that the stock price behaves something like this, and then suddenly it jumped like that. Okay, so this could happen, and we want to be able to capture that in our model, right? I mean, again, the question is, are you interested in this phenomenon or not? Are you interested in catching them or not? At the end of the day, right, the goal is to come up with, if you will, maybe a precise or a realistic volatility surface, right? Because your goal, if you're interested in pricing, then all you care for is somehow come up with a reasonable volatility surface, and you're done. So however much, right, components you want to add to your model is up to you. So you could, if you feel like the Black-Scholes model, right, the vanilla Black-Scholes model is enough to capture, right, whatever you want, the volatile surface, then you stop there. But you feel like, okay, it's not enough, I need to add more component, then you might want to go and try to capture the jump if whatever the underlying you're looking at has exhibits, right, jump phenomenon. Okay. So in this sense, it's very much like regression, right? You kind of add more explaining variables, but try to capture, right, all the variation in the model. But of course, you have to be careful because you don't want to over-explain the model. You don't want to just like kind of make a perfect fit, right? You just want to get to a reasonable, right, capturing of the pricing of the volatile surface, whatever that means. So, but here we're concerned with how to do so. If you are interested in capturing this kind of jump, right, how would you do so? The answer is you try to add one more component into the noise level, right? You add another noise component, right? But which is pure jump. So first, let me tell you what the model is. So the model looks just like Black-Scholes, but we have one more component like this. Okay, so gamma serves in a similar way as volatility. I'll explain. Here, ST minus tells you about the left-hand limit. Okay, left-hand limit of the stock price. This is the change in the Poisson process. N is a Poisson process. So there are several things to be understood about the new term here. So this is the new term, okay, which is the pure jump term that I'm talking about. So first, right, let's just see what it is, where NT is a Poisson process. And this is the Poisson lambda process. This is the most basic level, and we can modify the jump model, the jump source to incorporate more interesting behavior. But for now, let's just try to understand what it is. Let's see. Question. The NT, sorry, N is the standard expression for Poisson process. Yeah. Okay. Sure. So what is a Poisson process, right? So you see the working, the plan, right? The scheme is similar to what we did with Brownian motion. First, we need to define Poisson process. Then we need to understand the properties of Poisson process, including how to integrate with Poisson process. How to integrate. So it's very much like that idea of Ito, integral, Ito calculus in a way. But of course, I mean, like here is Ito in, parentheses because this is not Brownian motion, right? Ito is referred to that refers to a Brownian motion, so this is something else. But I'm just saying, like the idea is like we develop the stochastic calculus, except that there's no calculus here; it's something else. But I hope you get the idea. And then we would discuss, pricing formula, for example, and this include change of measure. All right. So first, right, what is a Poisson process? So NT is a Poisson lambda process if it starts at 0, just like Brownian motion, it starts at 0. And T has independent increment. Also, just like Brownian motion. So in other words, NT minus NS is independent of anything below S. Okay. So if you're familiar with Brownian motion, you will be familiar with this, right? It's exactly the same thing where we say that the future increment is independent of the past up to the present. So we can capture this by saying, right, this is the filtration at time S. The whole future increment is independent of the filtration up to this current time, current moment. So far, you can just say that these are the same properties as the Brownian motion. The one that make a difference is the distribution of the increment. The distribution of the increment, right? For Brownian motion, this will be right normal 0 t minus s. For Poisson process, it will be Poisson lambda t minus s. Okay, so this is what makes a difference. So in other words, Poisson and Brownian motion are both processes with independent and identically distributed increments. But they're kind of like at the opposite ends. The Brownian motion is normal, so it's continuous. The Poisson process is Poisson, so it's discrete, okay? Because Poisson random variables only take on discrete values. So that means that, right, if you were to graph the Poisson process, you see that it starts at 0. It will continue for a little bit, and then it will jump. It will jump to 1. And then it will continue for a little bit, and it will jump to 2. And then so on. Is that okay? And the convention is value is after the jump. So this is right continuous with left limit. All right. So the Poisson process jump with size 1 at a time. And the waiting time, right, in between the jump is a random time. So if you call this tau 1, right, how do I want to call this? Tau 1, tau 2, tau 3, right? So the taus are the time where the Poisson process jump, right? Then the tau I are random, okay? Random variables. Tau I plus 1 minus tau I has an exponential lambda distribution. Okay, so in other words, the waiting time, right? Tau I plus 1 minus tau I is the waiting time until the I plus 1 jump from the I jump. Is that clear? Is that okay? But right? Basically, the Poisson process is flat in between. The Poisson process is flat in between. Okay. Unlike the Brownian motion where it goes everywhere like this, right? The Poisson process is flat in between. It only jumps occasionally. So you see that when we incorporate something like this, right, into our stock model, what is the effect? So let's try to understand this, okay? And let's try to understand the technical part about the ST minus. So something like this, okay? ST minus will be the limit. Let's say as U goes to T from the left. S of U. So the reason is this. What happens is because the convention is we let the Poisson process be right continuous with left limits, right? So if you were to look at the Poisson process, NT1 minus here would be 0, right? So NT1 minus, N tau 1 minus would be 0. And tau 2 minus will be 1, right? Notice that N tau 1 is 1 and N tau 2 is 2. Is that clear? Right? The value of the Poisson process at tau 1 is 1. The value of the Poisson process at tau 2 is 2. But, right, the left-hand limit is 1 less. The left-hand limit is 1 less. Is that okay? So here, right, when we do this, what we mean is the left-hand limit before the Poisson process jump. Okay, so roughly speaking, what happens is this. When you construct a stock model like this, right? So let's suppose this is the Poisson. So this is tau 1, okay? And let's say it takes so long to run, and then there's tau 2. Like this, okay? This is NT. What does your stock price do? Your stock price starts at somewhere up to the first time that the Poisson process jump, dNT will be 0 up to this time. So there's no term like this. So up to that time, your stock just behaves like a usual Black-Scholes model. Okay. Then at the tau 1 moment, the Poisson process jump, which will induce a jump. Sorry, this is gamma, right? Which will induce a jump in your stock, all right? The jump size is this much. We'll talk about that later, okay? But basically, it will induce a jump. But the jump in your stock will not be 1, will not be value 1. It will be a different value. But it will induce a jump. And then from tau 1 to tau 2, there's nothing going on. So it will continue to move like a Black-Scholes model. And then at tau 2, again, the Poisson process jump. So it will induce a jump in your stock. Again, some jump, maybe, right? So here the jump will be higher, and then we'll do something like that. Is that okay? So the incorporation of the Poisson process into the entire model what happens is it when the Poisson process not jumps, then the stock would just move like a Black-Scholes model. But at the jump point, then the stock will also jump with a particular size. Okay, what size is the jump? What size is a jump? Well, the clue is given right here. So let me first write this, right? ST jumps when NT jumps. Okay, that's what it says. That's the first thing about this model. Second, right? So NT, right, always jump with size 1. Good question, Sherry. Very good question. And that's actually what we're going to address next. By definition, the Poisson process always upward jumping, always jump by size 1, right? And because the stock inherit that, and because the stock price is always positive by definition, right now our model only allows for upward jumping. Good question. Yes. But of course, right, this is unrealistic because, right, sometimes stock jumps up, sometimes stock jumps down. We will discuss how to extend the model to allow for downward jump. But for now, right, I'm just concerned with the mechanics on how to incorporate all this structure together. So let's just, stick with upward jump. But then, yes, right, yes. So, but it's important that you see why the jump is only up now, right? So NT always jump with size 1, that's by its definition. But the stock price, right? How much does ST jumps? ST jumps, right, with size. What size? Well, you see, right, where the stock jump, where NT jump, the stock jumps. And right here is a recipe. What it says, right, basically is ST minus ST minus, this is DST, is equal to gamma ST minus, right, DNT, but the DNT here, right, which is NT minus NT minus, which is a fancy way to write 1. Are we okay on this? So this right here is the jump size. And so the answer is the jump size is gamma times ST minus. Do you understand? And so you see why we need a gamma here. Because if we don't have the gamma, basically the jump size is as huge as the stock price. So, basically, right? All right, let's go back and review it from another angle. First, I ask you to trust me on this, that I can do everything like this. So I can add the ST minus on everything and doesn't change anything. Okay. So basically, I just add a minus here. And actually, this is not strange because from the Monte Carlo simulation, if you look at how we simulate the ST with Black-Scholes, we always say that STI plus 1 is STI times something something. Okay, if you look at the code. So this is exactly ST minus because it's the left point before we go to the next point. So anyway, right, this doesn't change anything. But with that, what I do is I will do this. Okay. Okay. So what have I done? This can still be viewed as percentage return, right? Percentage return. Okay. Maybe I forgot to mention this, but when you deal with jump process, it's very helpful which is what we're doing now. It's helpful to think of two situations, always two situations. With jump or without. You always want to think of those two. What do I mean by this? It's exactly what I did up here. I say when it doesn't jump, this is what happens. When it jumps, this is what happens. When it doesn't jump, this is what happens. When it jumps, this is what happens. So you kind of isolate the jump points and kind of analyze at that point. But all in all, right? So basically, if you feel uncomfortable with this term, you can just think of when it doesn't jump, then this is just ST. Because right, when it doesn't jump, then it's continuous. Then this is just your usual. This is just your usual return without this. Does that make sense? When it doesn't jump, then these two don't happen. But when it jumps, then exactly the return is what? The return is this gap divided by the previous point, right? When it jumps, what is the return, right? So for example, if your stock price jump from 100 to 200, obviously anyone will see that the return is 100%. How? When you do 200 minus 100 divided 100, right? So that's exactly what is doing to the return. At this point, right? But all in all, right, what you look at in terms of the total structure is this is a normal, right? This is a normal random variable. So all it does is it adds one more component to your return to your return process. So this is one more component. Yes. And you see, without a gamma, suppose we don't have the gamma, then what are we saying? If we don't have the gamma, then we say that whenever the jump happens, what is our return? If gamma equals to 1, then what are we saying about the return? When the stock jump, when the jump happens, when there's some shock to the market, what is our return? If gamma equals to 1? 100%, right? Because notice this is a unit in percent, right? This is where, right, unit matters, right? 100%, right? So gamma times 100, right, is percentage return when the shock happens. Does that make sense? So that's why you need a gamma to tune it down. Because you see, right, if you make the gamma, if you don't have a gamma, then every time it jumps, you have like 100% return, meaning your stock price will double. Yes, and that's right. I never seen any event. I guess probably it happened with the GameStop stock. I think it did double. Who knows? But right, generally when we see a shock, maybe it's a 5% jump or something, right? What we mean by shock is a non-continuous movement, right? We don't necessarily imply that a shock must carry with it a large jump size. That's up to you to model, right? But by shock, we only mean a non-continuous movement, right? A sudden jump in stock price. How large? Up to you. So you could choose gamma to be 0.05, so 5%, right? Jump, right? Of course, again, it's rigid. We're saying that every time it jump, it must jump by 5%. We'll fix that. Okay. Yeah, go ahead. What question do you have? Lee?
Professor, can you hear me right now?
Yeah, sure.
So how do you derive the second equation from the first one? Because you just subtract st minus, right? But
You mean
how
how
do
do I
you?
derive from here to
Yeah,
here? Oh, I
yes.
just divide, I divide both sides by st minus.
So should it be just plus the gamma and minus the nt?
Oh, no. So the minus here goes with the t. It's not st minus dnt. The whole structure is a product.
Oh, I see it.
So,
I see it.
so this is a product.
All right.
Okay.
Thank
The
you.
minus is goes on the t to denote the left limit, meaning it denotes the before t. So it's like the limit from the left of a function, right? So when we say, for example, right here, right, nt minus is 0, so the minus belongs to a time. Okay, yeah. So it's all a product structure. Why do we want a product structure? We want a product structure, so exactly like your question, when we divide, we get a return structure. We get a return structure that's purely influenced by noise and time. That's all, right? That's what we want. That's the essence of Black-Scholes model. Okay. All right. So that's the meaning of gamma, right? We need the gamma to tune down the return when the shock happens, or tune up if you like that. So one more parameter, right? The meaning of lambda. Lambda, right, tells us, remember, right, NT is a Poisson lambda process, right? But you don't see lambda explicitly in the graph. It's there implicitly, actually, right? Lambda is here, but it's implicitly. So lambda, right, tells us how often the jump happens. Okay. So frankly, right, because let's say N1, the Poisson process at one unit of time, could be 1 year, 1 month, depending how you call your time, right? NT has a Poisson lambda, right, times 1, right? T minus 1 minus 0 is 1. If you want to be pedantic, is this, which is Poisson lambda process. So expectation of n, right, 1 is lambda. So lambda tells you how many jumps you have in 1 unit of time, right? Lambda is average number of jumps in 1 unit of time, or if you will, is a jump frequency, right? The higher lambda, the more jump you will see. So this again, right, gives you more parameters to tune your model to see if you can catch whatever you are looking at. So let's take a look, right, at the simulation that we posted, right? Let's look at that again. So you see, right, here I let my sigma, the O volatility, to be 0.3, the gamma to be 0.1, so that's 10% jump, right? Lambda is the rate, so right now it's 0.2, so roughly I have 2 jump per 10 unit of time, okay? And notice that I simulate, right? You see, this is the percentage return simulation. The next one, right, is the previous one, stock price, right, times 1, because like basically it's just you have to add the previous, right, and then mu dt, sigma dwt, gamma dnt. That's all. Where what is dnt? dn is just Poisson lambda, right? Poisson lambda times dt. Okay. So this is exactly what we did before, right? This is exactly what we did before. So oh, sorry. So this is not even, sorry, this is not return, right? This is st plus 1 divided by st. So the percentage return will be this divided by this, subtract 1. That's why there's a 1 here, right? That's a percentage return. Anyway, right, let's look at the graph. You see, the Poisson process goes like this, jump by 1 and then jump. Where the Poisson process jump, right, the stock jumps. But the size, right, is decided by the stock. Notice you see here, you see how the jump size is kind of small here and the jump size kind of big here for the stock. Why? Because the stock is small, right? The stock is small here. It goes down here. So that's why even when there's a jump up, it's not that big. But here, right, the stock is big. But notice that both of these are 10%. Both of these are 10% of the stock at that time. Okay. To compare with, right, the model, the good old Black-Scholes model. So here I take the jump component away. You see it moves, so the path is exactly the same, right? I mean, not exactly, but it's very similar. But you see the overall effect, right? This is 0 to 180, 0 to 140, because the jump, right, kind of modulate that. So let's run again, right? And notice, first of all, if I run again with the same parameter, this will change. You see? Suddenly I pick up more jumps. It's randomness, right? On average, I should have, again, you know, 2 jumps out of 10 units of time, but somehow I pick up more jumps here, right? And look at this, I have more jumps. Okay, and some of the jump I think is hard to detect for some reason. And compare with, right, the stock without jump is less. I would say this is more volatile, right? Run one more. Again, right, go back to this. One more. Only one jump. Only one jump in this case, right? Only one jump. So, and you see here, you see the stock go from 100 to 300, where, oh, I guess this is volatile on both then. Let me change, right? Let me change the lambda to, let me change the lambda to 1, okay? So here I will make the stock jump more often. Let me change it to 2 to show you. If I change it to 2, you see it jumps a lot. Right here, see? Lots and lots of jumps. So the jump size is the same, but I make it jump a lot because I say that basically there are 2 jumps per unit of time, right? If I make it to 5, oh my gosh, you'll see it jump like a rabbit, right? You see? So this is probably unrealistic, but that's changing in lambda. So I would say maybe 0.2 seems reasonable. If I make the gamma to be big, watch out, right? Look. You see, stock price go to 5,000. Why? Because every time the jump happens, it jumped by 100%, right? While here is only 300. So clearly gamma to be 1, making gamma 1 is unrealistic, right? So we need to modulate the gamma. Like that, right? So that's more reasonable, right? If there's a jump, it's only 5%, so maybe even too small for us to catch with the eye. Any question? All right, so let me ask you this, right? So in a model like this, what's the volatility of the stock? In a model like this, what's the volatility of the stock? Is it sigma? What's the volatility of the stock? Is it sigma? Well, yeah, go ahead.
My guess is that gamma like contributes to the volatility like in a positive way. I'm guessing it goes up, but I don't know like the exact formula.
Good, good. So you have good intuition, but how do you carry it out in math then? What is the definition of volatility?
Uncertainty or risk, I guess. I don't know.
That's not precise.
Uh,
What is definition of volatility? Volatility is the standard deviation of return divided by time.
yeah.
So it's actually, right, volatility, if you will, is standard deviation of dst over st. Of course, right, in practice, what people do is people take the variance of some kind of return divided by t. Right? But you can kind of see that these two, and take the square root, of course. Sorry, square root up here, right? But you can see that these are roughly equal. All right. So if we look at this, right, what is the standard deviation of this guy? Or what's the variance of this guy? Well, the variance of this guy, I hope is clear, is sigma square. Oh, sorry. Yeah, sigma square plus gamma square times lambda. Why? Because so hold on, right? So maybe I should do this times dt. Okay. All right. So let me do it more carefully here. So no, this is also divided by dt. Sorry, right? Divided by dt. So what happens, right, is when we have this dst over st minus is mu dt plus sigma dwt plus gamma dnt, right? What do we have? Wt, right? dwt is a normal with mean zero and variance dt, right? dnt is a Poisson with mean, well, with rate lambda dt, right? So the variance of this guy will be the variance of this, which is sigma square dt, right? And then the Poisson. What is the variance of a Poisson? Variance of Poisson lambda is lambda.
Lambda. Okay.
So that's why it's gamma square, right? Where we pick up the gamma from here, times lambda dt, right? And so if you take the variance divided by dt, right? Or I mean, like, I hope that is clear then that the volatility is square root of sigma square plus gamma square times lambda. Is that okay? That's the volatility. That's a new volatility. Of course, right before, when lambda equal to 0, if you want, or if gamma equal to 0, that means there's no jump, then this return back to sigma. But right, that's the new volatility. And of course, right, I still use the same idea. Maybe I'm very sloppy here. I should do this, right? Variance of this and then square root. So I should do this. It's the whole square root. Right, that's volatility. That's the rate of the square root of the rate of the variance. right? But like what I want to say is having a precise definition of volatility, right, helps you to calculate it rather than just kind of expecting that it's greater. Because I'm sure maybe you probably did not have a lambda in mind, right, when you think of the volatility. Is that okay?
Yeah, that makes sense. Thank you.
Sure, but it also has an interesting effect that you see, of course, when we see if gamma is big, then the volatility increase. That's kind of clear. But it also says that if lambda is big, then also it contributes to the volatility of the stock. Does that make sense? Sure. If you have more jump, right, with the same gamma, I think anyone would say the stock is more volatility or more volatile. Is that okay? So right, so when adding a noise component, you change the volatility or you increase the volatility if you fix the sigma. Also, anyway, right, you change the volatility structure of the stock. Okay. All right, so 7 minutes. So I think I'll just tell you what's coming up, all right, and we'll do it next class. But so coming up, that sounds like a show. So coming up, what we'll do is from here, right, we need explicit formula for ST. Right? Remember, for example, I write something like this. What is ST then? What is ST, right? Because with the Black-Scholes, I have ST to be S0, right? Something like this. Now, with jump, how does that work? With jump, how does that work? Right? Second, I need martingale property of ST. Again, right, with Black-Scholes, I know that E to minus RT, discounted stock price is a martingale. Sorry, right, under P tilde. So actually, I need to change this to R and argue that it's discounted, right? So with the jump, actually, I have to say, right, that this is golden, meaning I cannot change this. Discounted stock price is always a martingale. Why? Because that's how we observe the stock price, right? The stock price, the fair price of a share in the future is the price today. So this is a golden statement that cannot be changed. It's independent of the model. Okay, so we still need this. Okay, but then of course the question is, what is P tilde? What is our P tilde now? Because now, right, what happens is we incorporate one more source of noise, the Poisson. And right, as Sherry observed, the Poisson always jumps up. Now, I hope, right, with Professor Larson, you learned that if something always going up, it cannot be a martingale. Why? Because a martingale has constant expectation. If something goes up, right, always has a tendency to go up, then it cannot be a martingale. So something must be modified in terms of the Poisson to turn it into a martingale, right? So there's that part. And so what is our P tilde? And then from there, right? And then of course it kind of is connected back to the explicit formula for the stock. And of course, finally, then if we put this together, we get pricing, right? Basically, formula for option. And then if we feel like it, we can talk into some kind of PDE structure. But it's not going to be a PDE here. It's going to be partial differential difference equation. So PDDE, partial differential difference equation. So it's not like I'm repeating myself, but it's really two different terms. The differential here refers to the Brownian motion structure. And the difference here refers to a structure of the Poisson because it's discrete. So it cannot be a differential equation, but it's a difference equation. Okay. So yeah, I mean, all these will be the program for next week. I will stop here. All right. So what I'll do now is I'll try to break you into different rooms, breakout rooms. Let me see. There are 14 of us. Okay. So you will be in your own room. You can take 1 or 2 minutes break or 5 minutes break if you will. The exam is already on Canvas. Okay. It'll be live at 10. You can go to Canvas, midterm 1, and look at and access the exam and start working whenever you want. I ask you turn on your camera, right? Once I change you to breakout rooms, only I will see your camera, no one else will see it. Okay. If you have any question, feel free to type into the chat and I'll address your question. Is that okay? So here we go. Okay, then Mushan.
Yep.
Okay. I think you're still in the main room, if I'm not mistaken.
All right. Sorry, I just have a question. So,
Sure.
when do we start?
10 o'clock. You can start whenever you want.
Okay, I can start 10 o'clock
already.
and it end at 11:40, right?
Or a little bit after that.
All right, cool. All right. Okay, I understand now. Yeah.
Sure.
Thank
If
you.
you have a question, let me know. Okay.
Yeah, can you assign another room for me? Thank you.
I'm not sure. Let me see. I think I can. Let me see here. More breakout rooms.
Oh, actually, I can rejoin the room. Don't worry about it. Okay.
Yeah, you can join the room. Yes.
All right. Thank you very much. Yeah.
Sure.
Bye.
Yeah.